Ground bars serve as central connection points for equipment grounding conductors and bonding jumpers, ensuring a low impedance path to ground, which is crucial for personnel and equipment safety, as well as for effectively dissipating fault currents. According to the National Electrical Code, ground bars are mandatory in electrical closets that house transformers, switchboards, panel boards, busways, and generators. Typically, equipment grounding conductors from all equipment within the closet, bonding jumpers connecting metal enclosures, raceways, and other non-current carrying conductive parts, and the grounding electrode conductor, when required, all connect to the ground bar. Consider a scenario where an electrical closet contains a 208 volts Y/120 volts bus duct riser but no transformers. In this case, a ground bar is not strictly required. This is because the busway, bus tap, distribution panel, and panel boards are already grounded through equipment grounding conductors run as part of the distribution feeders. However, when an electrical closet houses a 480 volts Y/277 volts bus duct riser along with transformers every 5 floors, installing a ground bar on the floors with transformers becomes a necessity. The ground bar offers a convenient spot for connecting the grounding electrode conductor. On floors without transformers, a ground bar might seem unnecessary, especially if the grounding electrode conductor can be directly connected to the building steel, assuming the steel is properly grounded and electrically continuous. Nevertheless, it's a good practice to install a ground bar even on these floors to maintain consistency and to provide a handy point for connecting equipment grounding conductors and bonding jumpers. Ground bars should be made from copper or an approved copper alloy, and their size should be appropriately selected based on the number of connections they will accommodate. The installation location should be visible and easily accessible. It's important to ensure that all connections to the ground bar are made securely, using a torque wrench or a similar tool to achieve the correct tightness. Implementing ground bars is a beneficial design practice that contributes to enhanced electrical safety and reliability, even in situations where the installation isn't strictly mandated by the electrical code. To delve deeper into the specifics, consider the components and connections within these electrical closets. Firstly, the equipment grounding conductors are essential for providing a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices. These conductors connect to the ground bar, ensuring that any fault current can safely flow back to the system ground. Secondly, bonding jumpers play a critical role in maintaining electrical continuity between metal parts such as enclosures, raceways, and other non-current carrying conductive components. These jumpers connect to the ground bar, minimizing voltage differences and reducing the risk of electric shock. Thirdly, the grounding electrode conductor connects the ground bar to the grounding electrode system, which could include building steel, a ground rod, or a ground ring. This connection is vital for stabilizing the system voltage with respect to earth and providing a path for dissipating ground faults. Now, let's examine the different scenarios in more detail. In the scenario without transformers, the equipment grounding conductors from the busway, bus tap, distribution panel, and panel boards are connected to the main grounding bus in the electrical service entrance. Since these components are already grounded, adding another ground bar may seem redundant. However, it's worth considering the benefits of having a local ground bar for future modifications or additions to the electrical system. In the scenario with transformers, the ground bar serves as a central point for grounding the transformer enclosure, the secondary neutral, and any other equipment in the closet. The grounding electrode conductor connects the ground bar to the building's grounding electrode system, ensuring a solid connection to earth. On floors without transformers, the decision to install a ground bar depends on the availability of building steel and the ease of making connections. If the building steel is readily accessible and properly grounded, it can serve as a suitable connection point for the grounding electrode conductor. However, if the building steel is not easily accessible or its grounding integrity is questionable, installing a ground bar provides a more reliable and convenient solution. In addition to the above considerations, it's also important to ensure that the ground bar is properly sized to accommodate all the required connections. The size of the ground bar should be based on the number of conductors that will be connected to it and the ampacity of the largest conductor. The ground bar should also be made of a material that is compatible with the conductors that will be connected to it, such as copper or aluminum. When installing a ground bar, it's important to follow the manufacturer's instructions and the requirements of the National Electrical Code. The ground bar should be securely mounted to a non-combustible surface and should be accessible for inspection and maintenance. All connections to the ground bar should be made using appropriate connectors and should be taught to the manufacturer's specifications. Furthermore, it's essential to consider the overall grounding system design when deciding whether to install ground bars in electrical closets. A well-designed grounding system should provide a low impedance path for fault current to return to the source, minimize voltage differences between metal parts, and protect personnel from electric shock. Ground bars play a crucial role in achieving these goals by providing a central point for connecting equipment grounding conductors and bonding jumpers. In summary, while ground bars are not always required in electrical closets, they are a good design practice that can enhance electrical safety and reliability. When deciding whether to install a ground bar, it's important to consider the specific requirements of the electrical system, the availability of building steel, and the overall grounding system design. By carefully evaluating these factors, electrical engineers and contractors can make informed decisions about the use of ground bars in high-rise buildings. Now let's talk about best practices. Firstly, always consult with a qualified electrical engineer or contractor to determine the specific grounding requirements for the electrical system. Secondly, ensure that the ground bar is properly sized and made of a compatible material. Thirdly, securely mount the ground bar to a non-combustible surface in a visible and accessible location. Fourthly, use appropriate connectors and torque all connections to the manufacturer's specifications. Fifthly, verify the grounding system's integrity by performing regular inspections and tests. Sixthly, document the grounding system design and keep it up to date with any modifications or additions. Seventhly, provide training to personnel on the importance of grounding and the proper use of grounding equipment. Eighthly, follow all applicable codes and standards, including the National Electrical Code. Ninthly, consider the use of supplemental grounding electrodes, such as ground rods or ground plates, to enhance the grounding system's performance. Tenthly, implement a comprehensive grounding maintenance program to ensure the continued effectiveness of the grounding system. By adhering to these best practices, you can create a safe and reliable electrical system that protects personnel and equipment from electrical hazards. Let's shift our focus to the specific requirements outlined in the National Electrical Code. Section 250.24. It covers the grounding of service-applied alternating current systems. It mandates that the grounding electrode conductor be connected to the grounded conductor at the service equipment. This ensures that the system is effectively grounded at the point of supply. Section 250.28 addresses the use of bonding jumpers and provides guidelines for their installation and sizing. Bonding jumpers are crucial for maintaining electrical continuity between metal parts and reducing the risk of electric shock. Section 250.30 provides requirements for grounding separately derived alternating current systems, such as those supplied by transformers. It specifies that the secondary neutral of the transformer must be grounded and bonded to the transformer enclosure. Section 250.50 outlines the requirements for grounding electrodes and specifies the types of electrodes that are permitted, such as ground rods, ground plates, and building steel. Section 250.64 provides guidelines for the installation of grounding electrode conductors and specifies the methods for connecting them to grounding electrodes. Section 250.166 covers the requirements for equipment grounding conductors and specifies the types of conductors that are permitted, such as wire, cable, and bus bars. Section 314.40 addresses the grounding of metal boxes and conduit bodies and specifies the methods for connecting equipment grounding conductors to these enclosures. Section 408.41 covers the grounding of panel boards and specifies the requirements for connecting equipment, grounding conductors and bonding jumpers to the panel board enclosure. By adhering to these NEC requirements, you can ensure that the grounding system is installed correctly and meets the minimum safety standards. Let's now talk about some additional considerations. Firstly, it's important to consider the effects of harmonics on the grounding system. Harmonics are non-sinusoidal waveforms that can cause excessive current flow in the neutral conductor and increase the risk of overheating and equipment failure. To mitigate the effects of harmonics, it may be necessary to install a dedicated neutral conductor or use a harmonic filter. Secondly, it's essential to consider the effects of lightning on the grounding system. Lightning strikes can cause severe damage to electrical equipment and pose a serious threat to personnel. To protect against lightning strikes, it may be necessary to install a lightning protection system that includes lightning rods, surge protectors, and a dedicated grounding system. Thirdly, it's important to consider the effects of electromagnetic interference on the grounding system. Electromagnetic interference can cause malfunctions in sensitive electronic equipment and disrupt communication signals. To mitigate the effects of electromagnetic interference, it may be necessary to use shielded cables, filters, and a properly designed grounding system. Fourthly, it's essential to consider the effects of corrosion on the grounding system. Corrosion can degrade the performance of grounding conductors and connections, reducing their effectiveness and increasing the risk of equipment failure. To prevent corrosion, it may be necessary to use corrosion-resistant materials, such as copper or stainless steel, and to protect grounding connections from moisture and chemicals. Fifthly, it's important to consider the effects of vibration on the grounding system. Vibration can loosen grounding connections and cause them to fail, reducing the effectiveness of the grounding system and increasing the risk of electrical hazards. To mitigate the effects of vibration, it may be necessary to use vibration-resistant connectors and to secure grounding conductors and equipment to prevent movement. Sixthly, it's essential to consider the effects of temperature on the grounding system. Temperature changes can cause grounding conductors to expand and contract, which can loosen connections and reduce their effectiveness. To mitigate the effects of temperature changes, it may be necessary to use temperature-compensated connectors and to allow for thermal expansion and contraction when installing grounding conductors. Seventhly, it's important to consider the effects of humidity on the grounding system. Humidity can increase the risk of corrosion and reduce the insulation resistance of grounding conductors and equipment. To mitigate the effects of humidity, it may be necessary to use moisture-resistant materials and to protect grounding connections from moisture. Eighthly, it's essential to consider the effects of dust on the grounding system. Dust can accumulate on grounding conductors and equipment, reducing their insulation resistance and increasing the risk of electrical hazards. To mitigate the effects of dust, it may be necessary to clean grounding conductors and equipment regularly and to protect them from dust accumulation. Ninthly, it's important to consider the effects of chemicals in the grounding system. Chemicals can corrode grounding conductors and equipment, reducing their effectiveness and increasing the risk of equipment failure. To prevent chemical corrosion, it may be necessary to use chemical-resistant materials and to protect grounding connections from chemical exposure. Tenthly, it's essential to consider the effects of physical damage on the grounding system. Physical damage can break grounding conductors and connections, reducing the effectiveness of the grounding system and increasing the risk of electrical hazards. To prevent physical damage, it may be necessary to protect grounding conductors and equipment from physical abuse and to repair any damage promptly. Now let's talk about maintenance. Regular maintenance is essential for ensuring the continued effectiveness of the grounding system. A comprehensive grounding maintenance program should include visual inspections, resistance measurements, and insulation tests. Visual inspections should be performed regularly to check for signs of corrosion, damage, or loose connections. Resistance measurements should be taken to verify the integrity of grounding conductors and connections. Insulation tests should be performed to check for insulation breakdown and leakage current. Any problems that are identified during maintenance should be corrected promptly to prevent electrical hazards. Finally, remember that ground bars are just one component of a comprehensive grounding system. A well-designed grounding system should include all of the necessary components to provide a low-impedance path for fault current to return to the source, minimize voltage differences between metal parts, and protect personnel from electric shock. By carefully considering all of the factors discussed in this narration, you can create a safe and reliable electrical system that protects personnel and equipment from electrical hazards.